Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 51 on Convergence tests.
This lesson will introduce a collection of tests for determining when an infinite series converges or diverges. Not all of these tests are useful in all circumstances, and it takes some time to learn which test works when. But with a little bit of practice, you'll be discerning convergence and divergence in no time.
Our goal in this lesson is to determine convergence or divergence of a series based on a sequence a sub n. We're going to employ the strategy of comparison. That is, we'll work with some other sequence, say b sub n, that is larger than or smaller than a sub n. Or, instead of another sequence, we might use a continuous function that is related to the original sequence. This is the basis of our first test, the integral test, a test which has some complicated hypotheses. First of all, the sequence a sub n must be positive and decreasing. Subsequent terms get smaller. Second, we need to take that sequence and connect the dots, turning it in to a continuous function, a of x, that is itself positive and decreasing and which agrees with the sequence at every integer point. If we have both of these, then we can compare the series, the sum of the a sub n's, with the integral, as x goes from 1 to infinity, of a of x dx. And these both have the same convergence or divergence. If one converges, so does the other. If one diverges, so does the other. Now, in terms of applicability, this test is not stellar. It has some strict hypotheses. And in terms of ease of use, this is also not the simplest test, since improper integrals can be tough. Its overall usefulness is limited, but there are several key examples where it works well. Why does this test work? Well, we've seen it in use once before when we determined that the harmonic series diverged. We compared it to the continuous integrand 1 over x. We saw, by taking a left Riemann sum, that the series was bounded below by the improper integral. If instead of a left Riemann sum, we took a right Riemann sum, then we get a bound in the other direction, that the series, or at least the tail, ignoring the first term, bounds from below the improper integral. Having this bound on both sides means that the series and the integral have the same convergence or divergence properties. If we look at a few examples, we'll see better how to apply this. Consider the absolutely fundamental series, sum from 1 to infinity of 1 over n to the p, where p is a constant. This should remind you of the p integrals from when we did improper integrals. In fact, these are called the p series. And the right way to understand their convergence or divergence is to compare to the integral as x goes from 1 to infinity of 1 over x to the p dx. Now we know that these p integrals converge when p is strictly greater than 1 and diverge when p is less than or equal to 1. Therefore, the same holds for the p series. This is a set of examples you must memorize. A related example that is shown in the same manner is the sum of 1 over n times log of n to the pth power. If we continue this to the function 1 over x times log of x to the p, then we can integrate that with respect to dx and obtain an integral using a little u substitution to get log of x to the 1 minus p over 1 minus p. Evaluating those, we see that again, we get convergence when p is bigger than 1 and divergence when p is less than or equal to 1. Thus, the same convergence and divergence holds for the series. And in both these cases, we have a range of convergence for p where it's strictly greater than 1. Our next test is a comparison test between two sequences. The hypotheses are relatively simple. We have two sequences, a sub n and b sub n. Both are positive, and the b sub n's are bigger than the a sub n's. If this is true, then what can you say about the series? Well, if b sub n is bigger than or equal to a sub n, then the sum of the b sub n's is bigger than or equal to the sum of the a sub n's. That much is clear. But what can we say about convergence or divergence? Well, because all the terms are positive, if the larger of the two series converges, then the smaller one must converge as well. Now, the converse of this is not necessarily so, but the contrapositive is if the smaller series diverges, then so does the larger. Now, in terms of applicability, well, this one doesn't have so many hypotheses as the integral test. But in terms of ease of use and usefulness, well, it's not perfect, in part because it's easy to get these two results confused, and it's sometimes difficult to pick the appropriate b sub n or a sub n, or to know which is which. Let's see this in the context of some examples. If we look at the sum as n goes from 0 to infinity of 1 over quantity 4 plus negative 1 to the n to the n, that's 1 plus a third plus 1 over 5 squared plus 1 over 3 cubed plus 1 over 5 to the fourth, etc. That's a funny looking series, but it's not that hard to figure out because if we call these terms the a sub n's, they are definitely bounded above by a sequence b sub n given by 1 over 3 to the n. Summing that up gives us a geometric series, which definitely converges. Therefore, the A series converges as well. Now, one of the problems is no one told us which is A, which is B, and what we should use. We could have bounded the A sub n's by a P series, where P, in this case, is equal to 2. That P series converges, and so the comparison test would tell us that the original series converged as well. On the other hand, a perfectly good upper bound is given by 1 over n. However, this P series diverges, and it doesn't tell us anything about whether the A series converges or not. This is the subtlety in using the comparison test. P-series tend to be extremely helpful when using the comparison test. Consider the sum from 0 to infinity of cosine squared n over 1 plus the square root of n cubed. Let's let that be our a sub n. We can bound the numerator from above by 1, since cosine squared is always between 0 and 1. What can we do with that denominator? Well, the denominator is strictly larger than n to the 3 halves. Therefore, we can bound this A sequence by a B sequence of the form 1 over n to the 3 halves. Since we know something about the P series for P equals 3 halves, we know that the larger series converges, therefore the smaller A series converges as well. Now let's see an example where it runs in the other direction. Consider the sum over n of 1 plus square root of n over square root of 1 plus n cubed. Now, if we let that term be our a sub n, then we can bound the numerator by, let's say, 2 square root of n, and the denominator by square root of n cubed. Now, that's going to give us a b sub n that is a p series with p equals 1. That is not going to help us. That series diverges. It doesn't tell us anything about the a series. So what are we going to do? Well, we implicitly assumed that our given was the a, but there's no reason why that has to be the case. Let's let this be the b terms, and we can choose an a term that bounds from below, taking a numerator of square root of n and a denominator of, let's say, 2n cubed. Then we get a lower bound for the b terms. Since the a terms give us a p series with p equals 1, the a series diverges, and thus does the b series diverge as well. Now, another example leads us to some complexity. If we let a sub n be 2n cubed plus 3n minus 8 over n to the fifth minus 5n cubed minus n squared plus 2, then what are we going to choose when we try to do the comparison test? Well, we need to bound the numerator from above. Let's say 2n cubed. No, that's not going to work because we've got the 3n. Let's say 3n cubed. That will do the job. The denominator, well, we can bound from below by 2n to the fifth. No. N to the fourth. No, that's not going to be good. That gives us a harmonic series for the b sub n. That diverges. This gets very complicated. Maybe the comparison test is the wrong one. Instead, let's try an integral test. Who wants to integrate 2x cubed plus 3x minus 8 over x to the fifth minus 5x cubed minus x squared plus 2? Hello, class? Where'd everyone go? Well, what are we going to do in this case? Asymptotic analysis is going to save us, as it has done so many times before. Taking this a of x, we see that the leading order term is 2 over x squared. Everything else is in big O of 1 over x to the fourth as x goes to infinity. Well, the same thing holds for the discrete setting with our sequence a sub n. Since the leading order term is a p series with p equals 2, we know that that converges. Therefore, we know that this series converges because we know the leading order term. That's the idea behind our last test in this lesson, the limit test. The limit test says if you have two positive sequences that have the same asymptotics, the same leading order term, specifically if their limit of the quotient as n goes to infinity is some number that is strictly between 0 and infinity, then these two series have the same convergence or divergence behavior. This is a wonderful test, very easy to apply and to use, and its overall usefulness is very high as well. Let's see some examples where we compute the leading order terms, just as we did with improper integrals. Consider the sum over n of log squared of quantity 1 plus 1 over n squared. That looks very complicated to figure out. I don't want to try an integral test with that. I don't know what to compare it to. But I do know the Taylor series for log of 1 plus something, where that something is very small. I know that the leading order term for this sequence is 1 over n squared, quantity squared. That is 1 over n to the fourth. That's a p series. With p equals 4, it converges. Thus does my original series converge. Here's another crazy-looking example. We'll put a polynomial on top and something with some square roots in it down below. All we need to do is compute the leading order term. For the numerator, it's an n squared with a 3 in front, but forget about the constant. In the denominator, the leading order term is n times n to the 5/3. When you get the exponents right, you see that the leading order term is 1 over n to the 2/3. That's a p-series with p equals 2/3. Forget it, that diverges. And so does the original series. Lastly, consider n times pi to the n over the hyperbolic cosine of n. Well, the leading order term in hyperbolic cosine is exponential in n. Therefore, with a little bit of factoring, we see that the leading order term is n times pi over e to the n. This definitely diverges. Always look to compute the leading order term.
All of the tests that we've considered in this lesson are based on some form of comparison and ultimately reduce to finding the asymptotics, or leading order term, in the sum. Isn't it a good thing that we're familiar with asymptotics from earlier in the course? In our next lesson, we'll look at a different collection of tests, ones that are based on the geometric series.